All right, so moving on to lesson 3.3, we're going to talk about the rules of logarithms, and obviously I'm still not able to hook up to my computer with my iPad, so we're just going to have to do this like we did in 3.2. All right, so I'm just going to go through the PowerPoints that I have. I'm just going to write down the important stuff, talk about it, do the examples, and then we'll move on. All right, so section 3.3 talks about the rules of logarithms. And so we're going to learn the rules of logarithms. We're going to estimate a large number. We're going to change the base of a logarithm. And we're going to apply logarithms in growth and decay. So it first starts out with the rules. And so we have our product rule, which, remember, logarithms and exponents are inverses of each other. Well, they share kind of the same rules. When we dealt with exponents, we said when you multiply with like bases, you added the exponents. Well, it's kind of the same thing here with logarithms. When you multiply, you can separate them by taking, notice it's log base b of m times n. So you're going to take log base b of the first, so m, plus log base b of the second, so the n. And so we can separate them by multiplying. And a good example might be like if I had log base b, log base 7 of 5x. So that means we would take log base 7 of our first number plus log base 7 of the last thing that's being multiplied there. Now, be careful on these because I did this example kind of on purpose there. If you have the log base of a number, you always need to see if you can simplify that, okay? So watch out for that. All right, then we have our quotient rule. Our quotient rule says that if we have log base b of two things being divided here, just like with the exponents, when you divide, you subtracted the exponents. Well, here when you're dividing, you're going to separate it by taking that log base b of the top minus log base b of the bottom. So if we had log base 2 of 9 over z, then I could separate them as log base 2 of the top minus log base 2 of the bottom. And then, of course, because it's log base 2 of 9 right there, I would have to check to make sure that it did not simplify, and it doesn't. And checking is just like what we did in 3.2. You would set it equal to y, change it to exponential, and see if you could solve it. And then we have the power rule. Now, the power rule is a little different. We didn't really have anything with exponents in it. What it is it says if I have log base b of m raised to the r, so it's raised to some exponent. The power rule says I can move that exponent to make it a constant in front that's being multiplied by its log. And of course, we can work the other way. If I have a constant in front of the log that's being multiplied by it and I need it to be removed or gone, then I can move it back as an exponent. So I can go both ways on that. So let's see, a good example might be if I had log of x squared. I could take that 2 and move it in front of its log to make that 2 times log of x. Or if I had 7 log of, that's not a good example. Let's do 2 log of 7. Then I could take this 2 and move it over here. So that's the log of 7 squared, which I could actually even simplify more. So that's log of 49. And so those are your three main rules for logarithms. Okay, so example 1 tells us, given that log base 5 of z is equal to 3 and that log base 5 of y is equal to 2, we're going to evaluate each expression. And a is log base 5 of y times z. Well, we notice that these are being multiplied, and we know we can separate them because when you multiply, you add. So this is saying each of them are going to get the log base 5, so log base 5 of the first, plus, because it was multiply, log base 5 of the second, so the z. And then, according to what it told us in the directions here, we know that log base 5 is equal to 2, plus, we know log base 5 of y is equal to 2, plus log base 5 of z is equal to 3, and then we know that 2 plus 3 is 5. All right, B B wants us to find log base 5 of 125y to the 7th. So the first thing we notice is that this is 125 times y to the 7th. So we're going to separate them, and because they're being multiplied, we separate them by adding. So log base 5 of 125 plus log base 5 of y to the 7th, sorry. Alright, so remember earlier I told you that if you had log base anything of a number, you need to check that out. So I'm going to come over here and I'm going to work on that. So that's log base 5 of 125, and it's in log form, so I'm going to set it equal to y. And then just like we did in 3.2, I know it's log base b of x equals y, and I'm going to change it to exponential. So my base is 5. Let me move my little think bubble down a little more that way. Base is 5, my x is 125, and my y is y. So when I set this up in exponential form, I get b to the y equals x, and then 125 is 5 to the 3rd. The one-to-one property says we can get rid of our bases because they're the same, and so we know that's equal to 3. Because that's equal to 3, I'm going to put that in its place. So I know this is 3 and then plus. Now this log base 5 of y to the 7th, I can't do anything with it until I move that 7. Well, this is where that power rule comes into play, because now we're going to put that 7 in front of its log. And so we're going to end up with 7 times log base 5 of y. Well, we can't add 3 plus 7 because the 7 is being multiplied, and PEMDAS tells us we have to deal with multiplication before we deal with addition. So I'm going to keep this as 3 plus 7, but we know that log base 5 of y was equal to 2. And so now I can work this out. So this is 3 plus 14, which is 17. Alright, using the same direction, so I'm going to move on to C. So I'm going to erase what I've got here. I'll do C right there. So C said we're going to take log base 5 of the square root of z divided by y. Well, the first thing is, remember we had talked about that the square root is the same as writing it to the 1/2. So this is the same thing as saying log base 5 of z divided by y raised to the 1/2. And so I can use that power rule now, and I'm going to move this 1/2 in front of its log. So I have 1/2 times log base 5 of z divided by y. And then we can work on the log part here. We know we have 1/2 times, but these are going to separate into two different things, and it's 1/2 times both of them. So what I'm going to separate, I'm putting in parentheses, and then I'll worry about the 1/2 in a little bit. Alright, so because z is being divided by y, when we divide to separate it, to expand it, we're going to subtract. So we're going to take log base 5 of the top minus log base 5 of the bottom. Well, so then I have 1/2 times. I could distribute the 1/2 if I wanted to, but we already know what log base 5 of z is. It told us in the directions that's equal to 3, minus, we know that log base 5 of y is 2, and so we can just work this out. So 1/2 times 1, which is 1/2. And then moving on to D. Let me erase what I have over here now. Alright, so for D, we have log base 5 of z to the 1 over 30, y to the 5th. Alright, we know that what's in parentheses there is being multiplied, so we can expand this. When they're being multiplied, we're going to add them. So this is log base 5 of the first plus log base 5 of the second. And then both of those have exponents, so we can't do anything until we move the exponents. So we're going to Bungee and move them in front of their logs. And so we got 1 over 30 times log base 5 of z plus 5 times log base 5 of y. Well, we know we got 1 over 30 times log base 5 of z is 3 plus 5 times log base 5 of y is 2. And so when I multiply 1 over 30 times 3, I get 1 over 10. Plus 5 times 2 is 10. And so when I add those together, I get 10.1, 10 and 1/10, something like that. And so there is example 1. And now I'm going to go ahead and end video 1 here. And we're going to start, we'll work out some stuff here in just a minute in example 2 on the second video.